Hello, this is Elnar de las Peñas, and in this video we're gonna solve problem 7.2 about stress, specifically lesson 5, the plane stress and transformation. But before we delve into our problem, let's have a quick review first on this lesson. So plane stress and transformation is characterized by 6 independent normal and shear stress components which act on the faces of an element of material located at a point. The general state of plane stress at a point is therefore represented by a combination of 2 normal stress components and 1 shear stress component which act on 4 faces of the element. So as you can see, this is the plane stress on xy plane and its orientation. And with it, we have obtained these equations. And incorporating these equations, we arrive into these transformation equations in which we're going to be using, particularly in this type of problem. So without further ado, let's get into our problem. We have 2 members of uniform cross-section, 50 by 80 millimeters are glued together along plane A-A that forms an angle of 25 degrees with the horizontal, knowing that the allowable stresses for the glued joint are 800 for the normal stress and 600 kPa for the shear stress. Determine the largest centric load P that can be applied. So first thing is to create a free body diagram for us to further understand the problem. We have our plane stress on xy plane as shown, and since the glued plane A-A forms an angle of 25 degrees from the horizontal, so we have this orientation that indicates our normal and shear stress. Then taking the angle perpendicular to the incline by subtracting 90 degrees with 25 degrees, we obtain the angle theta of 65 degrees. Since the pressure in this member only acts downward, so the stress along x-axis will be equaling 0. The stress along y-axis is equal to pressure over area. The shearing stress will also be equal to 0 and our angle equal to 65 degrees. So since we are going to find P, so we will use the transformation equations shown earlier. We have the normal stress of the plane equal to the stress along x cosine squared theta plus stress along y sine squared theta plus 2 times shear stress sine theta cosine theta. And since the stress along x and shearing stress are both equal to 0, so we are left with the stress equal to stress along y, which is pressure over the area times sine squared of 65 degrees. Then derive P using this equation. So we can now get P equal to the area times the normal stress over sine squared 65. Now let's substitute the given values considering its units. Like for the area, since the given was in millimeters, then we need to convert it to meters, as well as the stress given from kilopascal to pascal. So we now got the P of 3.9 times 10 to the power of 3 newtons. Then let's also use the shear stress equation in getting P. We have shear stress equal to the quantity of stress along x minus stress along y, sine theta cosine theta plus shear stress multiplied by quantity of cosine squared theta minus sine squared theta. And again, since stress along x and shear stress is 0, then we are left with shear stress equal to positive stress along y-axis, which is the pressure over area times sine 65 degrees and cosine 65 degrees. So derive P from the equation, then we have P equal to the area times shear stress divided by sine 65 and cosine 65. By substituting the given values considering its units, then we get P of 6.27 times 10 to the power of 3 newtons. And since the allowable value of P is the smaller of the 2 load values obtained, hence our P is equal to 3.9 times 10 to the power of 3 newtons, or just 3.9 kilonewtons. So that's pretty much it. Thank you and God bless.